Hey everyone, welcome back to the channel. I hope you guys are doing extremely well. So in this video, we are going to learn about detecting a cycle, yes, cycle, in an undirected, very important, in an undirected graph. So in this video, we will be learning how to solve this using BFS. In the next, we will be learning how to solve this using DFS. Now, till now, you have seen how to use BFS in order to solve matrix related problems or how to traverse in a graph. But how do you detect a cycle? So if you remember the definition of a cycle, you start from a node and you go and you go and you go and you go and you come back to the same node. So if you are able to come back to the same node, then only we say that the graph has a particular cycle. So how do you detect a cycle? But before that, let's do one thing. For this particular graph, create the adjacency list. If you don't know what is an adjacency list, lecture 2 or lecture 3. So what is BFS? So this is how the adjacency list will look like. So we're going to detect this using BFS. What is BFS? It is nothing but a traversal technique where you start from a node and you visit all the nodes in that graph. So if you are starting from this node 1, yes, what do you visit in the next step? You visit 2, 3 because they are at a distance of 1 or level 1. At the next step, you visit 5, 6, 4. Why? Because they are at a distance of 2. If you see, they are at a distance of 2. At the next time, you visit this 7. So this is what the BFS traversal is. It goes in level wise, like level 1, level 2, level 3. So basically, it visits simultaneously these 2 nodes, then these 3 nodes, then this node. This is what we call as BFS traversal, whereas DFS is different, where you just go. So you go basically, okay. What is the intuition of the algorithm? Let's understand. So we know BFS is nothing but a traversal technique, right? So imagine the first thing is 1, where you started. From 1, where do you go? You go to 2, you go to 3 at the same junction. Remember this. From 1, you go to 2 and 3 at the same junction because they are at level 1. So you went to 2 and 3, but remember this. You came from 1. You came from 1 to 2 and 3 separately, but you went into 2 and 3 because they are at the same distance or the level 1. Now from 2, where can you go? So if you carefully see, from 2, you can go to 1 and you can go to 5. But will you go to 1? Dude, you just came from 1 only. So why will you go back to the guy from whom you came? You need to do a traversal. So apparently from 2, you can go to 5. Right? So from 2 you can go to 5. So from 1 you came to 2, from 2 you can go to 5. Now there is something as 3. If you remember, we had 2 and 3. From 2 we went to 5. But now where will you go from 3? From 3 you can go to 6, you can go to 4, you can go to 1. But why will you go to 1? You just came from 1, right? So you'll go to 6 and you'll go to 4. So apparently the 2 and 3 went to 5, 6, 4. Went to 5, 6 and 4. And remember this. From 2 you went to 5. Okay. And from 3 you went to 6 and 4. Correct? So if you carefully see from 5, where can you go? You can go to 7. You can go to 2. But from 5, why will you go to 2? Because it is nothing but where you came from. So you will try to go to 7. And when you try to go from 6, you'll never go to 3 because you came from 3. And you again go to 7. So there are 2 guys who are actually going to the same place. But if you remember, when you started, you went in different directions. Now, how did you arrive at the same position? That is only because it is cycle and it is connecting. This is how the BFS will work. So I hope you have got the intuition. The intuition is very simple. You started in 2 different paths. And now if you are colliding in some portion, that will only be because there is something as a cycle. So what does the BFS algorithm state? If you remember well enough, the BFS algorithm, the first step of the BFS algorithm is define a queue and insert the first node. So this is the first node or the source node with the parent. You need to remember where it came from. Very important. So I can say it came from 0 or -1. That is your choice. It came from -1. At the same time, you need to create a visited array. Do you remember? Yes, you have to. It's like 1, 2, 3, 4, 5, 6. So it's like 1, 2, 3, 4, 5, 6, 7, and all of these will be marked as 0 apart from the guy 1. So this is how the visited array will look like. Okay, which one is your source node? The source node is 1, correct? So 1 is visited. So what you'll do at the first step is you'll take this one out. So you'll take this one out and you will say this came from nowhere, that is -1. It did come from nowhere, that is why -1. Let's remove this. So you have 1. Where can this one go? It can go to 2 and it can go to 3. How will you know this? You will go to the adjacency list and you will see what it is stored. And you see 2 and 3 are stored. So you can go to 2 and you can go to 3. So you go to 2 and you say it came from 1. You go to 3 and you say it came from 1. So 1 can go to 2. So mark it as visited and put that into the queue. Then you can go to 3, mark it as visited and put that into the queue. Once this is done, we can just omit this. Perfect. Now again, get the next guy. Get the 2, 1. So we got the 2, 1. Perfect. So can I say 2 came from 1? It did. So from 2, where can you go? Again, go to the adjacency list and it says you can go to 1. But dude, I just came back from 1. Why will I go back to 1? I will not. So I'll just go back to 5. So I'll go to 5 and say visited and I'll insert 5 came from 2. Perfect. So 5 came from 2 and 5 is visited. Let's omit this. The next guy will be 3, 1. So 3 came from 1. See this. Observe this. 3 came from 1. From 3, where can you go? You can go to 1, but you came from 1. You can go to 4. Yes. You can go to 6. Yes. So apparently you can go to 4 and 6. So you can go to 4 and you can go to 6. From 3, you can go to 4, mark it as visited, and 4 came from 3. You can go to 6, mark it as visited, and 6 came from 3. Perfect. This is also done. What is the next step? Next step is to get the 5, 2. So there is 5 which came from 2. From 5, where can you go? You can go to 2 as well as 7. But you just now came from 2. So you'll not go. So you'll try to go to 7. So you will go to 7. So 7 came from 5. So you went to 7. Perfect. And now omit this. At the next step, you get 4, 3. So you get 4 and it came from 3. So 4 has just 3 as the neighboring node. So it came from 3. So it will not do anything and it will omit this. Next, there is 6 and it came from 3. Important part. Important part. Very, very important part. Where can 6 go? 6 can go to 3, but it came from 3. 6 can go to 7. But if we go and see in the visited, it says, hey, we have already visited 7. But BFS tells me, but we traverse always in equal direction. How can someone visit 7? It can only happen if someone touched it right before me. And now if I go and touch it, it means it's a cycle. Someone at a level 2, and now I'm at a level 2. Someone right before me at level 2 touched the 7. And now I'm at level 2 and I'm touching it. Thereby there is a cycle. If someone has visited it, because we took 2 different paths, and if someone has already touched 7, it means it has a cycle. So we will say, yes, it has a particular cycle. That is how easy we can do this. So I hope you've understood this particular BFS algorithm. So we will now go back and try to write this BFS algorithm which detects a cycle. So let's code this up. So I'll be coding the C++ solution, and the Java solution as usual is on the left. You can follow it. So we're given the number of vertices or the number of nodes and the adjacency list. So what I'll do is I'll just have private function. I just want to write for a graph, okay, where we know that this is the source or something like this. So we have the source. Why am I writing like this? I'll tell you as we move forward, okay? Adjacency. So this is what I'm trying to write. And I'll write visited. We need a visited array as well. So please carry a visited array with it as well. So we will write something like visited of this source is equal to 1. We will declare a queue and it will have a pair of int, int. Why pair? Because you need to store where it came from, if you remember. And initially it was source and it came from -1 always. So we write something as not queue dot empty, which means let's traverse till the queue is not empty. We can say the node that we are currently standing is front dot first. We can say the parent is nothing but q dot front dot second. And once you have got both of these, you can always say q dot pop, right? Super simple. Now, what's the next step? You need to go to all its adjacent nodes. So please go to all its adjacent nodes. If the adjacent node has yet not been touched, no one has visited it, then I say, hey, listen, if it is not, let's visit this guy. Let's put this into the queue saying it came from node. Perfect. But what if it is visited? This is where we need to understand. So whenever we were at 5, we knew 5 came from 2. 5 came from 2, we know. And 5 had something as 2 as the first adjacent node. Remember, whenever you run the for loop, the first adjacent node will be 2. But will you say this 2 forms a cycle? No, no way. Because you came from 2 to 5. So, but this 2 would have been visited because it has previously been touched. But not in something like this. Just because you came via that path, that is why this 2 was touched. That is why it was marked as visited. Right? But let's go to the other case. When you go to 7, from 5 to 7, 7 was unvisited. Thereby you went to 7. Thereby you had something like 7,5 because 7 was unvisited. Right? So if it is unvisited, you go and just put it in. But what if it is visited? Let's come to this. At 6, it came from 3. So 6 has adjacent node as 3. But this guy is visited because it came from 3. But why is this guy visited? Why is this guy visited? It did not come from 7. Why is this guy visited? If someone is visited, remember this, if someone is visited and it did not come from it, if someone is visited, that means it will come to else, and it did not come from it, which means it's not the parent, which means it is a cycle. If this guy is visited, it will come here and it's not the parent. How did it visit himself? That's because it's a cycle. Someone else touched it. And if it is a cycle, you say cycle. Or else, if you just go across and you traverse everything, something like, I'll give you an example. If you traverse everything in sense, imagine you have something like 0, 1 node, 2 node, 3 node, and over here at 4, you had 5, you had 6. Imagine a graph like this. What will happen is you'll start from the 0 node, then you'll go 1, 4, then you'll go 2, 5, then you'll go 3, 6, over. So if your queue, at the end you traverse everything and there is no guy who's previously visited and it's not the parent, then you say there is no cycle. So this is how you can always do from a source. From a source. Because over here, the source was 0. Over here, the source was 1. What if the graph is broken into multiple components? Please go back and watch the lecture connected components. Please go back and watch the lecture connected components. What if the graph is broken into multiple components? So something like this. Imagine 1, 2, 3. This is a graph. 5, 6, 7, 8, 9. So what will happen is, for the first time, when you call it from 1, it will go and visit this, then this, but it will not find a cycle here. Then you have to again call it for 2. But will you? There's no point. There's no point again calling for 2. Because if 1 went ahead and did a traversal of the entire thing and it did not find a cycle, calling for 2, calling for 3, calling for 4 will never be able to find it a cycle. Will it be? Obviously not, right? The next step is like, okay, fine. We go to then 5, 5, 6, no cycle. Then we call it for 7. Now 7 says I got a cycle. Yes, with the same method. So you need to call for this one once, you need to call for this one once, you need to call it for this one once. So apparently you need to write like in terms of whenever there is a problem of multiple components. Like if you see over here in the example 2, we have something like a multiple component thing. So what you need to do is, you need to always write something like this. For I equal to the start, like if the nodes are 1 based, you start from 1 equal to n and you go like I plus plus. Okay. And over here, what you do is you say if not visited, I, please call the detect cycle or whatever is your detect cycle and start the source with I. And if this is true, I will say, hey, listen, this came down as a true. So can you say that there is a cycle? And if you have visited all the components and you never got a cycle, you say false. This is the standard procedure to do for components. So what will happen is, let's analyze what will happen. For the first time, it is 1. So it will go for 1. I'll find that it is not visited because you will have a single visited array. Remember this, you'll have a single visited array with all marked as zeros. So it will, whenever it goes to 1 and it finds 0, it goes and calls the detect cycle. And the detect cycle will go and mark visit, 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 and visit. So all of these guys will be visited, correct? And it will not return a cycle. So apparently next time it will be 2. So 2 will be already visited. We've already visited the component that has 2. Next it will be 3, already visited. 4, already visited. 5, not visited. So go for 5. So you again call for 5. So 5 goes visit, visit. So 5 goes and visits it. No cycle again. So then I will increase to 6. 6 is visited. Then it will increase to 7. The moment it increases to 7 and calls it for 7, it gives him a cycle. It says, hey, it's true. We have a cycle if we start from 7. And it says true. This is how you check for components. So always remember, by the way, let's check out. Okay, so they have clearly used something like 0 over here. And it's a 0 based indexing. So what we can do is, we can declare something like visited of v. And we can mark it as 0. Okay, means all of them are non-visited. And we can say, since it's a 0 based indexing graph, something like this. If not visited of I, that means not visited. If, let's call the detect that we wrote. And now please go and detect from the source this, adjacency this, visited this. And if this is true, tell them that this is a cycle. And if none of them is true, tell them there is no cycle. We say a graph to have a cycle if any of the component has a cycle. Remember this. We say a graph to have a cycle if any of the components have a cycle. So let's quickly run this and see if it is running fine. Perfect. As you see, it is giving us correct answer. So if I discuss the time complexity now, can you help me analyze that? What will be the time complexity? How many nodes will we visit at the worst case? I can say this detect will be like n into all the adjacent nodes. N into, because it's going to visit all the adjacent nodes one by one. So for every node, for the first time, if I go back here, for the first time it will go here, then here, then here, then here, then here, then here. So can I say it's a summation of degrees? Remember the BFS algorithm. You should remember the BFS algorithm I taught you. So whatever time the BFS algorithm takes, it's going to take the same time, which is first it will be n things twice of edge. Why twice of edge? Because for every node, you're traversing for all its adjacent nodes. And the adjacent nodes is nothing but the degree. So the summation of all adjacent nodes is equal to the summation of degrees. Summation of adjacent nodes is what you're doing, which is equal to the summation of degree, which is equal to 2e in undirected graph rather, if you remember the first lecture. So n plus 2e. Are we using any extra space? If you carefully see, we're using a Q data structure. So somewhere around big of n, and then visited big of n. So yeah, we can just wrap it up to something as big of n. Now you might argue, but Striver, we are running a for loop. And for every for loop, we are calling it. No, you're not calling it for every for loop. You can just do a big of n, because for the first time when you called for this component, it went in. For 1 only it went, and it went like 4 times. It never went for 2, never for 3, never for 4. Once you called for 5, it went for 5 and it touched 6. Similarly, when you'll call for 7, it will touch this. It'll be like calls will go, but in total, the moment you touch everyone, there will be no more calls. So in summation, it's not like every time you're going like n. It's not like that. Okay. So that's why you don't need to complicate stuff. So you can just keep it simple and say that the complexity is near about n plus 2e. And if you want to include the component thing, we go of n. Because in overall, I'm going to touch everyone, which is going to take this. And then there's a for loop that is running. Not into, because overall, I'll make sure I take this, right? So that will be the time complexity and the space complexity for this one. So guys, I hope I was able to explain you how to detect a cycle in an undirected graph using BFS. Just in case I was, please make sure you like this video. And if you're new to our channel, what are you waiting for still now? hit that subscribe button, because that is the only thing that keeps me motivated to make these kind of videos. And yeah, with this, I'll be wrapping up this video. Let's meet in some other video. Till then, wait. Check out the DP series and the SD sheet. Till then, bye bye. Take care.